So good morning, everyone. Thank you for letting me presenting this work we conducted with Dr. Alexander Pacha. So semantic reconstruction of music with graph neural network. The idea of this work is that many OMR systems rely on a four-stage pipeline that's taught with image processing to make the content stand away from the background, and then uses a music object detector that often aim at detecting so-called music primitives, so atomic glyphs of the music notations, and associate them with size and position of this object. But to be able to read the music, to understand it, it's not enough, and we need to go through a semantic reconstruction stage where the relationships between those music primitives are, we find them, we learn them, and from these semantics, we're able to re-encode the music into its final representation. In this work, we focus on the semantic reconstruction specifically, and we uses the music notation graph to express it. Music notation graphs are a graph where nodes are the music primitives and their relationship the edges. And this task can be seen as a simple link prediction task because the object detector is then detecting the nodes of the graph. And what we need there is these edges that represent the relation between the primitives. These relations we focused on the syntactic ones, so to say the one that combine the object to form the nodes. So in the example here, you'll see that you have two 8 nodes, and to understand that one node is an 8 node, we need two relations and 3 primitives. To do that, and because we have then a graph, we use the graph neural networks. This class of machine learning model have shown state-of-the-art performances in the link prediction area, and they work by sending information of a node embedding and description through its neighborhood. And they use graph structure input to learn a node level description in our case. So to use graph neural network in an OM to reconstruct the semantics of the notation, this is the implementation and the architecture we came up with. The main challenge is to obtain a graph-like structure from the object detector. So to do that, the first part is to build a feature matrix, so to translate the information recognized by the object detector in a matrix. So we one-hot encode the label of the music primitives and also their size and position. And then we wanted to have an adjacency matrix to build a graph. Why do we need to build this adjacency matrix? Is because assuming everything is disconnected would not make GNN useful. They use the edges to transfer the information from a node to another. And a fully connected graph would be too demanding in terms of computation. So we use the observation that especially close music primitives are often related. So we'll build a KNN, so closest, we connected the closest music primitive together and then pruned this graph and normalized it to obtain a candidate graph that is an overcomplete music notation graph that contains its own truth, and it then fed into a model that will learn how to cut the extra edges we have in a candidate graph. Yeah, so the model is composed of a GNN and a classifier. The GNN learns nodes embedding, and the classifier will cut or not an edge depending on its endpoint embeddings. To evaluate this, we already talked about it a little bit. There is no good metrics, so we could use either binary classification metrics, imagining if an edge has been correctly cut or correctly kept, we can have a binary classification there, or we can use graph edit distances. Our ground truth is a graph, and what we predict is a graph. So we can count the number of steps that goes from one graph to another. And an interesting metrics here have been the music error rate, which is a graph edit distance divided by the amount of true edges, of edges that exist in the ground truth. Yeah, this enable to scale a bit with the size of the score to compare score of different sizes. But all those metrics can be tricked somehow. So we used three different one to compare the model. So to say, mostly the accuracy, graph edit distance, and music error rate. This is what our results can look like. So here we display the graph on top of the score. We aim at predicting the music notation graph. Yeah, you can see like some edge are missing, for example, in the between the beams and the fifth note. And we try to learn and predict on three different data sets you might know. So music graph, WoRMS, and Muskema++. Yeah, I want to mention also that we cut the score by measure on the WoRMS and Muskema data set to have some comparable result with music graph that is composed of scores that are one measure long. The score here are not that great in terms of music error rate, so it still contains a lot of errors, but we could improve that by using a model ensemble solution. So to say, different model would perform not evenly great depending on what we call the link type. So between two different music primitive type, some presented better result than others. So what we did was to train a set of, to use a set of model, and at test time, at prediction time, make all those model predict the music notation graph. And then we selected the edge depending on its link type, and we choose the prediction from the model that showed the best performance on that. Leveraging this, we obtained 6% music error rate, so it's an acceptable result. But the graph neural network did not perform as well as expected. And also we had a lot of trouble in the training because it's a very sensible, they are very sensible models. So the conclusion is that we obtain acceptable results, but it might not be the best tool for predicting music notation graphs. Yeah, so if you have a question, I think I've been a bit quick, but
You've been right on time. Thank you very much for a great presentation. And we can open the floor for questions. Okay, Yuri, go ahead, please.
Thank you for the presentation. I have a couple of questions, but I'm going to start easy. I would like to know how large the model is, how fast it runs. Is it something small or is it something massive? Is it like yeah, like
the model is not that big. Not I mean, what I can say, I mean, it will be open source, but it's 3 layers mostly. I mean, for those models or those one, the layer type might change, but it's 3 layers of graph stage GNN layers, and the final output size is 1024, and the in between representation are 248.
So I guess it runs fast. It's like a couple of milliseconds to do.
Yeah, the prediction is very fast. The training required a lot of epochs. We're talking about thousands, so it took time, but yeah.
Thank you. And just a quick question about this slide that you are currently on. I wasn't sure about the multiple models. I'm not sure if I understood it properly. Did you mean to say that like you tried having one model for all the edges and that didn't work as well as having separate models for separate edge types?
Okay, so the way we went to that is when we had a deeper look in the prediction of the model, we could I mean this is an information you have as input, like which link type you're trying to predict between not head and stem, for example, or something different. And because we observed these differences in the results, one solution to make use of it is to, at test time, make every model predict everything. And then you go through your graph again and you see like, okay, we're trying to predict something between a node head and a stem. We know that model 5 is the best for this, so we take its prediction and then we combine this.
Okay, yeah. So it's ensembling with like preferences. I was thinking more about having a dedicated model just for node-head black to accidental and a separate model just for node-head black to flag. You have not tried that. I'm just curious.
I tried it, not for long, just shortly. But the main issue with this approach is that graph neural networks, how they work is to take an embedding of a node, and when they learn at the next iteration, it's combine the information of the neighborhood and the node itself. So if the graph you build at first only contains relation between node head and stem, either you will have a large graph over your image, or you will not only have like 2 nodes or a few ones and not a lot of information to combine. So the results shown that having a large graph for this with different music primitives type was better to learn.
Okay,
For
it defeats the purpose of a GNN. Okay, thank you. That makes sense.
Do we have any other question? We have time for one more. All right, I'll go ahead and ask my own question then. So if I understand right, you use KNNs to construct the candidate graph. So I guess the question would be, and we see that there are some issues with like scaling it maybe and how inclusive it is. If we did maybe use some grammatical rules into the candidate graph generation, do you think that would be a bit more efficient? But also like complexity-wise, would it increase complexity?
The complexity would certainly increase, but it's not that of a problem, I guess. But by including grammar rules, we somehow did it at the pruning stage. So this kind of graph just, I mean, we do it after creating the KNN graph. So to say, when you have this neighborhood connected graph, we cut the link that will never be in an errorless music notation graph. For example, a relation between 2 node heads doesn't make sense in the definition of the music notation graph. So we cut those edges, and this is like using the grammar. But we can also imagine creating this first graph with the rules, and we haven't tried that, but it could lead to interesting lightweight graphs. I mean, we had to set a threshold to connect one element to its neighbors, like how many neighbors, and using the grammar could help to reduce this number.
All right, thank you very much. Thank you for a great presentation.